Hello class, welcome to Geometry Lesson 12.1, which is all about probability events. In this lesson, you are going to learn how to use relationships among events to find probabilities. Alright, so let's talk about example 1, finding the probabilities of mutually exclusive events. So mutually exclusive means that things cannot occur at the same time, okay? So they are two unrelated things. So let's say you roll a standard number cube once, and I know some of you are rolling your eyes at the term standard number cube instead of me saying dice, but I would come back at you guys by saying, if I said dice, you'd say, oh, but what if it's like a 12-sided dice? We're not talking about that. We're talking about the regular old 6-sided dice, okay? So I'm going to call it a standard number cube because you guys like to argue back. So you roll a standard number cube once. Let E represent the event roll an even number, and let T represent the event roll a 3 or a 5. Now notice, if I said roll an even number, that can't happen at the same time that you roll a 3 or 5, right? That's why those two things are called mutually exclusive. So letter A, what is the probability that you roll an even number or roll a 3 or 5? So first, let's figure out what's the probability of rolling an even number. So if it's a 6-sided dice, we have 2, 4, and 6. That's 3 options out of the total 6 options. So the probability of rolling an even number is 3 over 6, or I could say 1 over 2. I'm going to leave it as 3 over 6 for now. Then let's figure out what's the probability of rolling a 3 or a 5. The probability of rolling a 3 or 5, that's 2 out of the 6 options. When you have two mutually exclusive events, the way that you find the total probability is you actually add those two things together, okay? Mutually exclusive probability typically goes along with the word or, okay? So if you see or, chances are the two things that you're talking about are mutually exclusive. So let's add those two together. 3 over 6 plus 2 over 6 equals 5/6. That is my probability that I roll an even number or a 3 or 5. Okay? Then let's look at letter B. You roll the number cube once, the standard number cube once, I should say. What is the probability that you roll an even number and you roll a 3 or a 5? Well, you can't roll an even number and a 3 or 5 because 3 and 5 are not considered even. So the probability of this happening is 0 because it can't happen. You can't have both of those things occur at the same time. Okay, question number 1. A box contains 100 balls. 30 of the balls are Gauss purple and 10 are Fibonacci orange. If you select one of the balls at random, what is the probability of each of the following events? Start with just letter A. I only want you to look at letter A for now. Type that answer into the question on Edpuzzle. Good luck. Hopefully for letter A, you said Gauss purple has a 30 out of 100 probability. The orange, the Fibonacci orange, has a 10 out of 100 probability, which is 40 over 100. Or I can say that reduces to 2 over 5, or I could say 0.4, or I could say 40%, and my smartboard is going crazy. I am sorry for the ridiculous colors there. Okay, hopefully you got at least one of those answers. With probability, you can actually write it, unless I specify, any of those 3 ways. You can do the fraction, you can do the decimal, or you can do the percent. Okay? Now, go ahead and take a look at letter B. What is the probability the ball is not Gauss purple and not Fibonacci orange? Sorry, not and. Or not Fibonacci orange. Good luck. All right, for this problem, you either figured out, okay, there are, between the two, there were 40 total purple and orange balls, so that means that there are 60 that are not purple or orange. So you said 60% or 0.6 or 3/5. Some of you might have said the entire bag, so that would be 100% of the different colored balls minus the circumstance that we don't want. We don't want the purple or the orange. You took your answer from part A. That is possible. That is actually called a compliment. Not like, oh, you look so nice today. That's different compliment, different spelling. I know you guys are rolling your eyes at me, but hopefully that helps you remember. So a compliment is the other part of the set that like makes it whole. So if I'm looking at all of the purple and orange balls, the complement would be the rest of them that are not purple and orange, okay? So here's a nice little screenshot for you. It helps you figure out, if we're talking about mutually exclusive, how to find the probabilities. And then here's that lovely word complement I was talking about. The complements that I made fun of is actually spelled with an I instead of an E. So that helps you figure out the difference a little bit if you can remember that detail. Okay, so the complement of an event is the set of all of the outcomes in the sample space that are not included in the event. So like I said, we were looking at purple and orange, so it meant the complement was all of the other colors. All right, example 2. Find probabilities of non-mutually exclusive events. So a student-made target includes 2 overlapping squares. Assume that a sticky ball thrown at the target is equally likely to land anywhere on the target. What is the probability that the ball lands inside one or both of the squares? So as soon as you have things that are non-mutually exclusive, that usually means that there's an overlap somewhere. This is a nice example because there's a visual like overlap to help you understand. So the first thing you always want to do is figure out what is your total sample space. So the target is 20 centimeters by 60 centimeters. So I'm going to say the total is 20 times 60, which is 1,200, okay? Now I need to find the areas of the targets. Okay, so we have 2 squares that are the same size. They're both 10 by 10. So that means 10 times 10 is 100. And there's 2 of those, right? So 10 times 10 is 100, times 2 is 200. But then we need to account for this space right here that overlaps. It's the side length is 5 and 5. So 5 times 5 is 25. So the area of the targets is 200 minus that overlap, so 175. That means the probability of it landing in one of those 2 squares or the overlap is 175 over 1,200. And what I want you to do from there is you want to simplify. So I would ultimately simplify down to 7 over 48 if I kept going. For those of you that hate simplifying and you do it the long way by hand, let me teach you a quick shortcut. Type 175 divided by 1,200 into one of the handheld classroom calculators. Once you do that and you have a decimal, what you should do is you should hit second, and then there's a PRB button. And right above the PRB button in light blue, there's something that looks like something like this. And you've maybe never known what that means, but what that means is it'll take your last answer. That was unfortunate. It'll take your last answer and it'll convert it from either a decimal to a fraction, or if it was a fraction, it'll take the fraction and convert it to a decimal. So if you did 175 divided by 1,200, hit enter, you have a decimal. Hit second PRB. I believe it's right above that key. So if you do second PRB, enter, you should end up with this lovely fraction showing up on your calculator. If you need help with that, let me know. I'm certainly more than happy to help you with figuring out how to simplify things on your calculator. Okay, question number 2. Go ahead and read this problem and try to figure it out. Good luck. All right, to solve this problem, hopefully you started out by figuring out the total space. So 34 times 20 is the entire computer screen. And then you found out the area of the starship, which was 2 circles. So I did 2 times pi times radius squared, which is 72 pi. And then there's a 20 centimeter squared overlap. So on my calculator, I typed in 72 pi minus 20, put that in parentheses, hit divided by 680, and I ended up with 0.3032. And and I reread the directions, which said round to the nearest whole percent. So 0.303, that 3 does not bump up that 0. That means that it stays at 30%. So it's a 30% probability that the point will appear within the starship. Okay, so this is what we just talked about. We talked about how you kind of add things. You take your non-mutually exclusive events, add them together, and subtract the overlap. Okay? All right. Identify independent events. So first, let's start. We have a jar that contains 12 Play-Doh green marbles and 8 Gauss purple marbles. So letter A, a marble is chosen at random from the jar and replaced. Another marble is chosen at random from the jar. Does the color of the first marble affect the possible outcomes for the second marble chosen? Well, if I took something out of a bag and I put it back in and pulled from that same bag, I'm pulling from the same stuff each time. Like if I drew out a green marble the first time, I put that green marble back. So I still, on the second draw or the second pull, I still have 12 green marbles. So that means that the probabilities are the same. When you have independent events where you replace items, the probability is going to remain the same. Okay, letter B. A marble is chosen at random from the jar and not replaced. So a lot of you don't like to read the questions thoroughly. You like to kind of skim and figure out and kind of guess and check your way through the problems. Probability questions are not the place to do that, because if you skip that single word not replaced, that's going to change your answer. So we have another marble is chosen at random from the jar. Does the color of the first marble affect the possible outcomes for the second marble chosen? Okay, so that first example where we replaced it, those were two completely independent. The first draw did not impact the second draw. Now the second round, we are talking about we don't replace that marble. So that changes what the second person gets to pull from. So no matter what, the first person has 12 green and 8 violet. But let's say that a green marble was chosen first. Then the second pull only has 11 green and 8 violet to choose from. Or if they pulled a purple, we have 12 green and only 7 violet. So that totally changes the probability. So that is called a dependent event. Okay? Dependent is when you, when the first outcome changes the second, or whatever scenario you're talking about, changes or influences the probability of the second event. Okay, so the letter A was an example of an independent event. Letter B is an example of a dependent event. All right, question 3. There are 10 cards in a box. 5 are Brahmagupta black and 5 are Phidias red. 2 cards are selected from the box, one at a time. So if we talk about a card is chosen at random and then replaced, and then another card is chosen, does the color of the first card affect the possibilities of what the second card is? Good luck. Hopefully you said no, because they are independent events because we replaced that first item. So the sample set was the same the second time through. All right, so let's quickly talk about how to find the probability of independent events. Okay, so these are when you have that replacement scenario going on. So in this example, there are we have a dice or standard number cube and a coin. Okay, looks like we're looking at a regular quarter. Okay, so there are 6 possible outcomes for the dice, right? So let's say the probability of rolling a 4 would only be 1 out of 6. There's only 1 4 on that dice because it's standard. Okay, so what's the probability of rolling a 4 and flipping a heads? Well, if it's not a trick coin, it would be 1 over 2, right? So we're going to assume it's not a trick coin. And I'm going to say that in order to figure out the probability of both rolling a 4 and flipping a heads, I'm going to do 1 over 6 times 1 over 2. So the probability of getting a 4 and the probability of getting a heads, I multiply together. So the probability of both of those events occurring is 1 in 12. Okay, so when you are dealing with independent events, you are going to multiply the probabilities of each event together to find out the probability of both of the things, or maybe there's more than 2 things happening at once. Okay, so let's look at, this is our last example. Alex cannot decide which shirt to wear today, so she chooses one at random. Apparently she has a very small closet. She has 4 shirts, and looks like we have 2 are yellow, 1 blue, 1 green. Okay, so that's our first event, is Alex cannot decide what shirt to wear today. Aren't you guys glad you have uniforms? You don't have this problem. I know you guys are rolling your eyes and probably yelling at the screen right now. Anyways, the second event is the probability of rain today is 40%. Okay? 2 totally unrelated things, right? What you wear does not influence the weather whatsoever. So letter A, what's the probability that Alex chooses a yellow shirt and it does not rain today? So let's talk about the probability of Alex choosing a yellow shirt. So as I mentioned before, it looks like she has 4 shirts and 2 of them are yellow. Okay, so the probability of picking a yellow shirt is 1 over 2. Now let's talk about the probability of that rain. So the probability of rain today is 40%, but if I read the question carefully, it says it does not rain today. What's the probability it does not rain? Well, if the probability of rain is 40%, that means it's a 60% chance that it will not rain, okay? Which, if I simplify, that becomes 3 over 5. So then I move on over, and I want to figure out the probability of both of those things occurring at the same time. 2 independent events, I multiply them together. So I end up with 3/10, or 0.3, or 30%. Again, all of those are acceptable answers. Your book will usually tell you which one it wants you to answer with, okay? Then, letter B, what is the probability that Alex chooses a yellow shirt and it does not rain today? Or Alex chooses a green shirt and it rains today. Okay, so this one's the next level of complexity, because if we look, this whole thing right here is what letter A was. So we know the probability of that is 0.3. Now, remember earlier in this video when I told you, hey, if you see the word or, chances are you're dealing with some mutually exclusive stuff. So Alex can't choose both a yellow shirt and a green shirt to wear because, 1, there are no shirts that have both of those colors on them, and 2, we're talking about separate shirts here, okay? So she is not going to wear 2 shirts. We're going to rule that out as well. So these are 2 mutually exclusive events, and if the shirt one is too tough for you to comprehend, it cannot both rain and not rain, okay? It can go on and off like in the hour or the minutes, but overall, if we said it did not rain at all today, like we're going to assume it's an all or nothing thing, okay? So then our second thing that we have to find the probability of is Alex chooses a green shirt and it rains today. So let's find the probability of that quickly. There was only 1 green shirt in the closet, so I'm going to do 1 out of 4 times, because these are independent events, and it rains. The probability of it raining was 40%, which 40% is just the same as 2/5. So if I multiply those together, I get 2/20, or I get 1/10, which is 0.1. Now going back to this or, when you have mutually exclusive things, back in example 1, we added our probabilities together when things are mutually exclusive. So the probability that Alex chooses a yellow shirt and it does not rain today, or Alex chooses a green shirt and it rains today, would actually be 0.4, or 40%, or you could say 2/5. All of those are acceptable answers. If you have questions on that one, please be sure to reach out for some help. And go ahead and try this problem on your own. Good luck. All right, hopefully for question 4, you first figured out what the probability of spinning 2 blues would be by doing 1 over 3 times 1 over 3, because that was the probability of spinning a blue. So 1/3 times 1/3 gives me 1/9. Then you figured out the probability of spinning 2 oranges, so 2/3 times 2/3, that gives me 4/9. And then you said, hey, those two things are mutually exclusive. You cannot both spin a blue and an orange in the same spin. So 1/9 plus 4/9 equals 5/9. So the probability of spinning the same color twice is 5/9. All right, and for those of you that still do the screenshots of the concept summaries, here is a great concept summary. It helps you remember some of the symbols for it and the little details that go along with some of the vocab and problems. If you have any questions at all, please feel free to reach out for some help, and I'm more than happy to assist you.